somewhere in the water that pulls back and forth against the shore in the same wave that breaks across your foot at the edge of any beach in the world, there is gold. Real gold in solution, dissolved into the salt water the way sugar dissolves into tea, in such fantastic quantities that the total amount scattered across the world's oceans has been estimated, at the upper end of careful guesses, at around 20 million tons. That number is difficult to hold in the mind. 20 million tons exceeds the combined gold reserves of every nation on Earth. It is more, in raw quantity, than all the wedding rings, dental crowns, coins, circuit boards, religious icons, and Olympic medals that have ever been hammered, struck, or forged since human beings first learned to recognize the soft yellow metal in a riverbed. The oceans hold something on the order of 150 times all the gold that has ever been pulled out of the ground in human history. And no one has ever figured out how to get it. That's the riddle of this episode. The metal is there. We've measured it. We've published papers in respectable journals confirming the concentration and the chemistry and the distribution. The treasure is real, and the treasure is, in any meaningful economic sense, untouchable. The reason is dilution. Although 20 million tons sounds enormous, the volume of the ocean is more enormous still. Across all the water in all the seas, the concentration of dissolved gold is somewhere around 13 parts per trillion, about 1 gram for every 100 million tons of seawater. To picture it concretely, if you scooped out an Olympic swimming pool full of seawater and somehow filtered every gold atom out of it perfectly, you'd come away with less than 1/10 of a milligram of metal, less than the weight of a single grain of sand. The first chemist to detect this gold was a British researcher named Edward Sonstadt, who in 1872 published the first analyses showing measurable quantities of the element in seawater. His estimate of the concentration turned out to be many times too high, but the underlying finding was correct, and it set off 150 years of inquiry. A strange chapter in the history of chemistry opened with that paper, in which a series of brilliant minds and a few thoroughly fraudulent ones would devote themselves to the same impossible problem. Some would devise elaborate machines, others would charter ships and chase the project across half the world's oceans. One of them, the most accomplished, would carry the failure with him for the rest of his life, and several would simply lie about what they had discovered. Tonight, the story of an element that fell from dying stars, soaked into the rivers of an early world, was carried down to the sea by every storm that ran across the continents, and has been quietly waiting in the dark ever since for 150 years of human effort, all of it, so far, in vain. Every atom of gold that has ever been touched by a human hand was made before the Earth existed. The metal predates our planet, our sun, and the very oxygen our world breathes. Gold isn't a substance the Earth itself can produce. To make a single atom of gold, you need to fuse together 79 protons into one nucleus, and that's a feat requiring energies of a kind that only the universe, in its most violent moments, has ever been able to manage. The interior of even the hottest star cannot do it. Our sun, despite its fearsome appearance to us, is far too cool in the nuclear sense to make so much as a single atom of the metal. Whatever it produces by way of nuclear fusion stops at iron, which sits low on the periodic table. Where then, did gold come from? For most of the 20th century, astronomers believed it must be made in supernovae, the explosive deaths of giant stars, which are about the most spectacular events that ordinary stellar evolution produces. But supernovae, as the math came to show, don't quite have what it takes to make gold in the quantities we observe scattered through the galaxy. In August of 2017, in a galaxy about 130 million light-years from Earth, 2 neutron stars finished a slow gravitational waltz they had been performing for some 100 million years and finally collided. A neutron star, for those who haven't heard the term, is the leftover core of an exploded star, compressed to such an unimaginable density that a single teaspoonful of its substance would weigh roughly 1 billion tons. When 2 of them slam into each other, the resulting collision, called a kilonova, is among the most extreme events the universe ever permits. The gravitational waves it gave off were detected on Earth by the LIGO Observatory, and within hours, telescopes around the world were watching the light from the event itself. In that kilonova, in roughly the span of a few seconds, neutrons rained against atomic nuclei so rapidly and in such enormous quantities that elements heavier than iron, including the gold atoms involved, were forged out of nothing more than the simple ingredients of subatomic physics. The colossal explosion that followed threw those new atoms outward into the surrounding galaxy, where they drifted for hundreds of millions of years before finding their way into the slow gravitational gathering that would, in due course, become our own solar system. This is the story scientists now believe is responsible for most of the gold in your jewelry box. Some smaller portion of it may have come from rare supernovae of a kind called magnetorotational, which involve fast-spinning giant stars whose magnetic fields focus the explosion in ways that allow the same heavy element forging to occur. But whether gold was assembled in collisions or collapses, the broader truth holds. The gold in every modern bank vault was once, in its raw form, part of an explosion so enormous that the entire visible universe, when it happened, briefly grew measurably brighter. After that long cosmic journey, in the great forging of the early solar system, a particular quantity of those atoms got bound into the rocky material of the young Earth and, over the following 4.5 billion years, slowly worked their way to where they now wait, in the rivers, the rocks, and, most of all, dissolved into the water of the seas. When the Earth first finished forming, around 4.5 billion years ago, very nearly all of the gold it contained sank to the core. Gold is heavy, about 19 times denser than water, and during the planet's earliest molten years, it drained downward through the surrounding lighter material the way oil droplets sink through honey. The metal ended up locked away in the dense iron and nickel ball at the center of the world, which has been entirely inaccessible to us ever since. What was left at the surface, the gold we can actually reach, is, in cosmic terms, a kind of late delivery. Most geologists now believe nearly all of the gold currently in the crust and oceans arrived during a relatively brief period known as the Late Heavy Bombardment, when a swarm of asteroids battered the inner solar system about 4 billion years ago, planting their precious metal cargo into the outer few miles of every rocky planet they hit. From that point forward, the slow geology of the Earth took over. Hot rocks pushed up from below by volcanic activity were cooled, weathered, broken, and rebroken across the long ages by frost and wind and water. Whenever a gold-bearing rock was exposed to the open sky and the running stream, it began, in some small way, to dissolve. Rain, slightly acidic from the carbon dioxide it picks up while falling through the atmosphere, carried away trace amounts of metal from the rocks it passed over. Larger pieces of gold were transported as flakes and nuggets. These are the placer deposits that have made famous names of fortune out of California's American River, the Yukon's Klondike, and southern Africa's Witwatersrand. A smaller and stranger portion was carried in true solution, dissolved atom by atom into the running water and washed steadily downhill. Every river on Earth carries a tiny dissolved load of metals to the sea. The figure is so small that it would mean nothing on the scale of an individual stream, but the combined rivers of every continent, draining across 4 billion years, have delivered an extraordinary quantity of dissolved metal to the ocean basins. Some of that material precipitates back out into seafloor sediments. A portion is consumed by marine organisms and dragged down to the abyss in the slow rain of their dying bodies. The remainder stays in solution in the water column, where it has now been quietly accumulating for as long as there has been any water at all. Gold isn't the only metal delivered this way. Silver, copper, manganese, uranium, and dozens of other elements have arrived along the same routes. Each one comes to a different equilibrium with the seawater. A few are stripped out almost immediately by chemical reactions or by living things, while others, like sodium and chlorine, build up to enormous concentrations and give the sea its taste. Gold, for chemical reasons we'll get to, can stay in seawater for a very long time. It is part of the strange resident chemistry of the open ocean, neither quite at home nor quite ejected, occupying a sort of permanent middle state. The river route, slow and steady across geological time, is one way the metal arrives. The other way is far more violent, and only relatively recently has it been understood at all. At the bottom of the ocean, where the sun has never reached, and the pressure is so great that an unprotected human body would be crushed in seconds, there are places where gold pours directly out of the rocks. They were discovered in 1977, when a small American research submarine called Alvin descended onto the mid-ocean ridge near the Galapagos Islands. The scientists on board expected to find the same near-freezing, near-lifeless landscape that earlier dives to those depths had revealed. A sterile, slow place where almost nothing happens at all. What they encountered instead was a riot of biological colour around a series of chimneys spewing black, billowing fluid at temperatures so high it should have boiled the surrounding water. Around them, in the warm zone where the hot fluid mixed with the cold sea, lived the most concentrated communities of deep-sea organisms anyone had ever documented. Clusters of giant tube worms, beds of mussels, and clouds of swimming shrimp, all of them living off chemical energy in a world the sun has never lit. These chimneys are called hydrothermal vents, or, in their hottest and most spectacular form, black smokers. They form along the great seam of the mid-ocean ridge, where the tectonic plates of the planet are pulling apart and molten rock from below is rising toward the seafloor. Cold seawater drains down through cracks in the basalt, becomes superheated by the underlying magma to temperatures approaching 400 degrees Celsius and erupts back up through other cracks in the crust, carrying with it everything the surrounding rock has been willing to release. What the rock releases in those conditions is a great deal. Iron, copper, zinc, manganese, silver, and gold all become temporarily soluble in superheated seawater under enormous pressure, and the rising hydrothermal fluid is, briefly, almost a soup of dissolved metals. When that fluid finally meets the cold ocean above, the metals come crashing out of solution and precipitate as fine particles of mineral, forming the dark cloud of smoke that gives the chimneys their name. Over centuries, the precipitating minerals build the chimneys themselves, growing them upward at rates that can exceed 30 centimetres a year, until they topple under their own weight and the cycle begins again. Some of that precipitating metal is gold. In 2017, a team studying a vent field in the South Pacific called Newer South documented native gold particles in the venting fluid itself, confirming the long-standing hypothesis that the smokers were not just spilling dissolved metal into the surrounding sea, but actually creating tiny grains of solid gold in the rising plume, which then settle into the sediment around the vent. Certain hydrothermal sites have been measured with gold concentrations in their solid material that rival the richest land-based mines. Over the geological lifetime of the Earth, the smokers have built deposits called seafloor massive sulfides, knee-high to building-sized accumulations of metal-rich rock scattered across the mid-ocean ridges of every ocean. More than 400 such sites have been catalogued so far, and the total number is almost certainly in the thousands. They sit, on average, about 2 miles down. This is the most concentrated form of gold the sea contains, and like the dissolved gold in the water column, it's, in any practical economic sense, beyond reach. Mining at those depths would require equipment that has only recently begun to be developed. It would face vehement opposition from marine scientists worried about the vent ecosystems and the rare organisms that live nowhere else. Even in the best case, the ore would emerge at costs that may not compete with mining the same minerals on land. The vents will probably keep their gold. The first serious effort to extract gold from seawater was not really an effort, it was a swindle. In the late 1890s, a Baptist minister named Prescott Ford Jernigan, who had been preaching to small congregations in Connecticut and Massachusetts and was struggling to make ends meet, claimed to have received a vision while bedridden with typhoid fever. In the vision, he later said, God had revealed to him a method for drawing gold out of the sea. He called his invention the gold accumulator. It was, on the outside, an unimpressive thing, a wooden box with holes in the sides, containing a tray of mercury connected to a small battery. The idea was that the electrified mercury would, somehow, draw the dissolved gold out of the seawater that flowed through it. The box was to be sunk overnight, and the gold would be collected in the morning. To demonstrate the device, Jernigan partnered with a childhood friend named Charles Fisher. The two of them invited a wealthy jeweler from Connecticut, Arthur Ryan, to witness the process in Niantic Harbor on the Long Island Sound. They lowered the accumulator into the water, sat with Ryan through the night, and pulled the device up the next morning to find it filled with bright, unmistakable flakes of gold. Ryan was, understandably, persuaded. Ryan was also unaware that Charles Fisher was an experienced commercial diver. In the dark hours before dawn, while Ryan slept in the small wharf shanty the three men were sharing, Fisher had quietly slipped on his diving gear, swum out to the accumulator under the surface, and replaced the mercury inside with a salted version laced with gold flakes he'd previously purchased. By morning, he was back in the shanty, dry and snoring, while Jernigan made coffee and the device, already producing, was hauled up to general astonishment. What followed was one of the great financial frauds of the American 19th century. Jernigan and Fisher Incorporated as the Electrolytic Marine Salts Company raised what would, in today's money, amount to roughly $30 million from over 1,000 investors and set up a factory in the remote fishing town of Lubec, Maine. The location was chosen, ostensibly, because of its strong tidal currents, but actually because it was difficult for curious shareholders to reach. They hired more than 700 labourers to build out a second, larger plant, while continuing the swindle by simply purchasing gold in Boston and shipping it back to the factory each week, presented to the world as the latest harvest from the sea. In late July of 1898, when a former associate threatened to expose the operation unless he was paid off, Jernigan and Fisher refused and quietly fled. On the 31st of July, the New York Herald ran the story. By the time investors and labourers descended on Lubec demanding answers, both men were already gone. Jernigan with his family bound for France, carrying $150,000. Fisher headed for New Zealand with his own $100,000. The factory closed. The accumulators were assayed and found to contain no gold at all. Jernigan, surprisingly, would later send $85,000 back to the cheated investors, a partial restitution that puzzled everyone, including the people receiving the money, before disappearing for good. And for a brief, painful moment, the American public was forced to consider that the wealth they had hoped lay floating in the sea might not be so easily reached after all. It was only a brief moment, though. The lesson didn't last. 22 years after Jernigan vanished, an actual scientist, among the most accomplished of his century, set out to do what the pastor had only pretended to do. His name was Fritz Haber. He was a German chemist, Jewish by birth, who had won the Nobel Prize in 1918 for inventing a process that could pull nitrogen out of the air and fix it into ammonia. The Haber-Bosch process, as it came to be known, made cheap synthetic fertilizer possible on a global scale, and is sometimes credited with saving more human lives by the food it helped grow than any other single chemical innovation in history. Haber had also, more darkly, supervised the German army's use of poison gas in the First World War, and was widely regarded in the years afterward as both a scientific hero and a moral catastrophe, sometimes in the same conversation. In 1920, with Germany prostrate under the staggering reparations imposed by the Treaty of Versailles, Haber turned his attention to the sea. Reparations were to be paid in gold, and Germany had almost none. The wide-ranging estimates of 19th century chemists, taken together, suggested that the world's oceans might contain on the order of 65 milligrams of gold per ton of seawater, a concentration that, if accurate, would make industrial extraction economically promising. Haber, who was an expert in electrochemistry, believed he could design a process that would do it. The German government quietly funded the project on the understanding that, if it worked, the country might pay off its war debt with metal pulled out of the Atlantic. For 6 years, he worked on it. The German research vessel Meteor, on its great expedition across the South Atlantic from 1925 to 1927, drew seawater samples from every major basin and shipped them back to Berlin, where Haber's laboratory analysed them using the most careful techniques available. He developed new methods for the trace analysis of gold in salt water, methods so sensitive they would influence the chemistry of trace metals for decades after his death. He published the entire project in 1927 as a paper titled Über den Goldgehalt des Meerwassers, on the gold content of seawater, which remains a model of meticulous experimental chemistry to this day. The paper also documented the project's failure. Earlier estimates, Haber discovered, had been wildly wrong. The true concentration of gold in seawater was not 65 milligrams per ton, but, depending on the basin sampled, somewhere between 4 and 10 micrograms per ton, roughly 1,000 times less than what his project had been designed around. At that concentration, no chemical process available to humanity could extract the metal at anything approaching the price of gold on the open market. The project was, quietly, abandoned. Haber blamed himself. He felt he had failed his country at a moment when it most needed him, and the failure compounded what was already a difficult period in his life. His first wife had taken her own life some years earlier. His health was deteriorating. And in 1933, when the Nazi regime came to power, the man who had once organised Germany's wartime chemistry efforts was driven out of his own country for being Jewish. He died of heart failure in a hotel in Basel, Switzerland, on the way to a new appointment in Cambridge in January of 1934. Those who knew him reported that, even at the end, he occasionally returned to the question of the gold. To understand why 6 years of careful work by one of history's great chemists couldn't produce a single profitable gram of gold, you have to understand a little about how gold behaves in salt water. In its native form, gold is famously unreactive. It doesn't rust, tarnish, or combine readily with anything under ordinary circumstances. This is why ancient gold coins pulled out of shipwrecks come up gleaming, while iron objects from the same wreck have long since dissolved into rust-coloured stains in the sediment. Gold is the one common metal that the sea cannot quietly destroy. The same quality, however, also makes gold extraordinarily difficult to remove from seawater once it has gotten there. Most metals dissolved in the ocean are present as free ions, simple charged atoms that can be readily plucked out by the right chemistry. Gold is different. The trace amounts of it in the ocean are bound into complex molecules called chloride complexes, where each gold atom is surrounded by several chlorine atoms in a fairly stable arrangement. These complexes are chemically inert, electrically neutral, and remarkably reluctant to give up their gold to anything offered as an alternative bond. The very chemistry that keeps the metal stable on land, the unreactivity that makes it useful as jewellery, also keeps it locked into the seawater in which it floats. There is also the simple, brute problem of volume. The standard concentration of dissolved gold in seawater after Haber's correction and the further refinements that have followed in the decades since, is somewhere around 10 parts per trillion. To picture this in physical terms, a swimming pool of seawater contains, on average, less than 1/50th of a milligram of gold. Collecting a single gram would require processing roughly 100 million tons of water. The amount needed to make extraction commercially worthwhile exceeds what has ever passed through any human-built filtration system in the history of engineering. Even if a chemical process could be designed that worked perfectly, that captured every single atom of gold in every drop of water it touched, the energy required to pump that much water through any system would, by itself, cost far more than the gold would be worth. This is not a problem that can be solved by cleverness alone. It runs into the basic physics of moving liquids and the basic chemistry of unreactive metals, and those are walls that even Nobel laureates do not get past. There is one further complication. The deeper layers of the ocean contain slightly more gold than the surface because falling organic particles and slow chemical processes redistribute it downward over the millennia. But the deeper layers are also harder to reach. A practical extraction system would have to either lift enormous volumes of cold, high-pressure water from below, or find a way to bring the gold up without disturbing the conditions that keep it where it is. Neither is easy. The deep ocean is a stubborn place. Its chemistry holds. What Haber discovered, and what no chemist since has been able to overcome, is that the ocean is not simply a vault. It is a particular kind of vault, designed by the laws of physics, with a lock that opens to the wrong side. There is, of course, another kind of gold in the sea, not dissolved, but waiting in solid form, lost. The United Nations has estimated that there are at least 3 million shipwrecks scattered across the floors of the world's oceans. Of these, perhaps 1% have ever been examined by human eyes. The rest sit in the dark, in their own particular silences, slowly being claimed by the sediment around them. And a small but interesting fraction of them carry in their holds treasure that was being transported when they went down. The richest such wreck so far identified is the San Jose, a Spanish galleon sunk off the coast of Colombia in 1708 during a sea battle with the British. She was carrying gold, silver, and emeralds taken from the mines of South America to be shipped back to the Spanish crown. A cargo that modern estimates, in present-day terms, put at somewhere in the vicinity of $20 billion. The wreck was located by Colombian researchers in 2015, but legal disputes over ownership have so far kept her treasure where it has been for more than 3 centuries, 2,000 feet below the surface. Other wrecks have given up their secrets. The SS Central America, an American steamer carrying gold from the California gold rush to financial centers in the East, went down off the coast of the Carolinas in a hurricane in 1857. About 425 people died and more than 2 tons of gold went down with them. The wreck was located in 1988 at a depth of about 1.5 miles, and the recovery efforts that followed brought up dozens of gold ingots, thousands of coins, and the personal effects of passengers who had been on their way home with their fortunes. The find was valued, eventually, at more than $150 million. The Atocha, lost off the Florida Keys in 1622 and discovered after 17 years of searching by the treasure hunter Mel Fisher in 1985, gave up many tons of silver and gold. Other ships have followed. The wider pirate vessel, the SS Gersopper, lost to a German submarine in the Atlantic in 1941. The 11 Spanish galleons of the 1715 Plate Fleet that went down in a hurricane off Florida, and various medieval Portuguese and Dutch carracks lost on routes nobody remembers. Over the past several decades, each of these wrecks has slowly returned its cargo to the surface as deep-sea technology improved. Marine archaeologists estimate that as much as $60 billion in precious metals may still rest, untouched, on ocean floors around the world. That number sounds impressive until you realize it is essentially nothing compared to the dissolved gold in the water itself. The wrecks are concentrated tragedies. Individual ships, crews, and cargoes lost on known dates in known waters, locatable on a chart if you have the right equipment. The dissolved gold is something larger and stranger. It's a kind of patient, distributed wealth that the planet has been quietly stockpiling since before any ship was ever built, since before there were people to build ships at all. And yet the wrecks are the only gold the sea has so far been willing to give back. The dream didn't die with Haber. After his failure, the question of recovering dissolved gold from seawater fell mostly out of serious science for nearly half a century. The math was discouraging. The chemistry was, by any practical measure, against you. Most researchers who thought about it concluded that it couldn't be done and turned their attention to easier problems. But the dream has a long memory. In 1941, a paper in the journal Nature described an electrochemical method for extracting gold from seawater. The method worked. It could, in fact, pull dissolved gold out of seawater under controlled laboratory conditions. It also cost, in energy and reagents, roughly 5 times as much as the gold it produced was worth. In the subsequent decades, a handful of other researchers, working quietly in university laboratories around the world, took up the same problem. None of them found a path to economic viability, but each of them moved the underlying science forward by some small amount. In the past 10 years, the work has grown more sophisticated. A class of materials called metal organic frameworks, crystalline structures with internal surfaces vast enough that a single gram of them, fully unfolded, would cover several football fields, has shown a remarkable affinity for gold ions in complex chemical mixtures. In 2018, an American chemistry team demonstrated that one such material, soaked for a single week in seawater off the coast of Jacksonville, Florida, could pull dissolved gold out of the water around it. The captured amount was tiny, about 1 part in 10,000 of the material's weight, but it was measurable. The principle, after 100 years of doubt, had been demonstrated under genuinely natural conditions. More recent work has improved the rates of capture by orders of magnitude. A Chinese team in 2023 developed a similar framework that could remove over 99% of dissolved gold from a treated seawater sample, spiked for the test with higher than natural gold concentrations, in under a minute. None of these methods yet would be profitable if scaled to commercial extraction from the open ocean. The cost of the materials, the slow rate at which gold atoms encounter them at true marine concentrations, and the enormous volumes of water that must be processed continue to keep economic extraction out of reach. What has changed in the past few decades is the broader context. With the rise of electronic waste, which contains its own significant quantities of gold in difficult-to-recover concentrations, the chemistry of gold capture has become a far more active research area than it ever was in Haber's day. Many of the same materials being designed for seawater extraction work even better on the more concentrated solutions left behind by the processing of discarded computers and phones. The lessons of the sea are quietly, gradually, helping with the more tractable problem of the trash. The ocean still holds its own gold, but the work of trying to reach it has made other valuable problems easier to solve. And every so often, in some seaside laboratory, a researcher leaves a small piece of polymer hanging in the surf for a week and pulls it back up to see what it has caught. Always there is a little gold, never quite enough. The dissolved gold in the world's oceans is not exactly lost. We know where it is. We've measured it. We can, if we work hard enough, pull a few atoms of it out of any sample of seawater we choose to examine. What we cannot do, despite 150 years of trying, is gather it. The sea holds it in such fine distribution, with overwhelmingly inert chemistry across impossibly vast volumes, that no human technique yet conceived can collect it at a price the world is willing to pay. The treasure is real, and the treasure is, in practice, sealed. This is a story, in some ways, about the limits of cleverness. Fritz Haber, who pulled nitrogen out of the air and changed the way the planet eats, couldn't pull gold out of the sea. The basic chemistry wouldn't let him. Wouldn't, in fact, let anyone. There is no clever trick that converts 20 million tons of dissolved metal into 20 million tons of usable bullion. The sea has had its gold for billions of years, and it gives the gold up grudgingly, atom by atom, into the bodies of organisms that live and die in the dark, or into the slow sediment of the deep basins, where the long geological cycle will eventually fold it back into stone. The treasure that fell from dying stars and was washed down to the oceans on every river that ever ran remains, after all our trying, almost exactly where it was when the first human looked out across the surf and wondered what the water might contain. And so the gold remains. The same wave that breaks across your foot at any beach in the world contains, in its small volume, a few atoms of the metal that human beings have killed and quarrelled and travelled across continents to obtain. They are there. 1,000,000 years from now, in the wave that will break against the same shore, they will still be there, untouched, waiting for nobody, simply present. Sleep now, if sleep is near. The water is calm, and the ocean still keeps its gold.